So here's the first question. A uniform magnetic field of 0.08 Tesla passes through a coil of 15 turns. So let's say you have a uniform magnetic field. So I'll describe it by using something like this. Okay, so this uniform magnetic field here is 0.08 Tesla. So I can label it as B is equals to 0.08 Tesla. And it passes through a coil of 15 turns with an area of 25 cm squared. Okay, so let's say your coil is in black color. So this is your coil, and there's 15 turns for your coil. Okay, then this coil here has an area which is 25 cm squared. And this, oh, okay, at an angle of 35 degrees. Oh, this is what I missed out. Okay, so this uniform magnetic field here is making an angle of 35 degrees. That means by my uniform magnetic field cannot be drawn like that. Okay, this is perpendicular right now. My uniform magnetic field cannot be drawn like that. I might need to draw it like at an angle. So something like this. Probably that's not the best way to view it. Let's try to draw it from another perspective. Let's say if you view it from this angle. Then what we will see will be wait, it's not working. Wait for a while, yeah. Okay, let's try to view it from this angle. If you view it from this angle, it's like this. Okay, so right now what I'm drawing is a circular plane like this, but what I'm going to do, I'm going to view it from this angle. I'm going to view it from this angle. So right now, my circular plane will be a straight line because it's just representing this plane over here. Okay. So this is my plane, circular loop. Then it's n equals to 15, and it has an area of 25 cm squared. Technically, they don't tell you whether the area is a squarish area, a rectangleish area, or a circular area. But I don't think it's a big problem to assume a shape. Okay, and you have magnetic field that is passing through an angle of 35 degrees. So this is your uniform magnetic field, and it's passing through this area over here with an angle of 0.08 Tesla, 35 degrees. Okay, just to remind you that this line that I draw here, it's representing this viewing it from the side view. Then what we see is just a straight line. Okay, so this is the diagram to represent the situation. So now they ask you to calculate the magnetic flux in the coil. So magnetic flux in the coil, they say magnetic flux, so it's only for one turn only. So it'll be phi. And you know that it's a dot product between B and A. Okay, in this case, B and A, BA cos theta. Okay, the magnitude of B, which is 0.08 Tesla, the area here is 25 cm squared. So we have to convert it into meter squared. If you are not confident, you can write it outside. You can do the conversion outside. You want to eliminate cm squared. You want to replace it with meter squared. So you eliminate cm once, you eliminate cm twice, you introduce meter, you introduce meter. 1 meter is equivalent to 100 cm. 1 meter is equivalent to 100 cm. So it's equivalent to 25 times 10 to the power of -4 meters squared. Okay, so you can write 25 times 10 to the power of -4 cos theta. Okay, so theta again is the angle between the magnetic field and the area vector. Your magnetic field, the direction is already labeled over here. And you know that the direction of the area vector, you can pick it either to be in this direction. This can be your area vector, or it can be in this direction, area vector. Okay, so which one should you pick? Like I said, it's easier to do your calculation if you pick the area vector to be the one that is in the direction of the magnetic field. So this one is opposite the direction. This one is in the direction. So you will pick the one that is pointing upwards. So you pick the one that is pointing upwards, and they tell you that this is 35°. So you know that the other side here will be 55°. And 55° will be the angle between the area vector and the magnetic field. So when you substitute in your angle, you substitute in 55°. Then if you calculate it, you'll be able to get your answer to be 1.15 times 10 to the power negative 4. 1.15 times 10 to the power of negative 4. Again, the unit is Weber. Okay, I think I should enlarge this diagram just to make it clear. Enlarge is usually ugly. Okay, so let me redraw the thing here. So this is your magnetic field here, and you know that the magnetic field has an angle of 35° with the coil. Okay, so it makes an angle of 35° with the coil. Okay, and you know that the area vector must be perpendicular to the coil, so it's either pointing upwards or pointing downwards. This is your choice for area vector, either pointing upwards or pointing downwards. But as I say, you are free to pick anything you want. You can pick the downward also can, you can pick the upward also can. But you just arrive at answer with a different sign. Okay, for now, I'm going to pick the direction that is having the same direction as the magnetic field. Okay, I don't want the one that is in the opposite direction. So this is opposite direction, this is same direction. So I pick the one in the same direction. So I eliminate the one that is pointing downwards. So this is my direction of the area vector. And my area vector compared to the magnetic field B over here, you can see that the angle in between them is 90° minus 35°. So it's 55°. That's why I substitute 55° over here. Okay, you must have to be very careful with the angle given in the question. The angle given in the question, it says that the magnetic field makes an angle of 35° with the coil. Magnetic field makes an angle of 35° with the coil. That's why my 35 is labeled over here. But when I do my substitution, it's the angle between the magnetic field vector and the area vector. So it's 90° minus 35°. Okay, so you have to be very careful with that. Okay, the next question asks what? The next question asks for the magnetic flux linkage. So this one is a very straightforward question. They want you to find linkage. So it's just N times phi. Okay, you don't need to go through the whole MBA course data process. You just need to take the number of turns, 15, multiplied by 5, which is 1.15 times 10 to the power of negative 4 Weber. Okay, so if you calculate it, I believe you're able to get the answer of 1.72 times 10 to the power of negative 3 Weber. Okay, it's still the same unit because the number of turns doesn't carry any unit. So the unit for magnetic flux linkage is also Weber. Nothing has changed over here. Okay, so yeah, this purpose of this question over here is to highlight to you that the angle, you have to be very careful when you're labeling the angle. It's always no harm to draw the diagram to see clearly where are all the angles and whether you are substituting in the right angle or not. Okay, so that's the first question.